The question that I have is, how do we handle composite distributed loading in analysis of structures? So we have results for a rectangle and a triangle, right? So let's see how we can apply these in order to deal with a distributed load that is represented by a composite area like this. In other words, we have an area here which is actually a trapezoid, right? But it could be represented by a rectangle and a triangle. So this is the sort of thing we need to learn to do in this course. So we go ahead and divide this trapezoid into this rectangle right there and this triangle. Now we treat these as two independent distributed loads. We have this triangular load which has its own resultant force F1, and it acts 1/3 from the base, right? So this is the base, this is the vertex, right? So 1/3 of 9 feet, which is the height of this triangle, right? And then we have this rectangular distributed load or uniformly distributed load, which has its own resultant force F2, and it acts halfway along the length, right? So this distance is going to be 9/2. So here are the calculations for the resultant forces. And of course, we recognize this distance right there is 100 minus 50, which is 50, right? And therefore, area under the triangle would be half times 50 multiplied by 9. And I get 225 pounds out of that. And the area of the rectangle is 50 multiplied by 9. And that gives me 450 pounds for that. So at this point, we know the magnitudes, we know the locations of each of these individual forces, right? Now you want to combine the two in order to come up with the total resultant force. So the total resultant force F would be equal to F1 plus F2, and its location, let's call it X naught. So in order to find X naught, we equate the moments one more time. So here are the calculations. So F multiplied by X naught. So in other words, we are taking moment from this point. F multiplied by X naught would be the moment of this resultant force, right? Which should be equal to the sum of the moments of individual forces. So that will be F1 multiplied by X1, which is this distance, plus F2 multiplied by this distance, X2, right? And therefore, X naught equals 1 over F times F1 X1 plus F2 X2. And F is 675 pounds. So you basically add the two forces, and we come up with 675 pounds for that. So 1 over 675 multiplied by F1, which is 225, times X1, which is 9/3, which is 3 feet, plus F2, which is 450, multiplied by X2, which is this distance right there, 9/2, which is 4.5, right? So you simplify that, you come up with 4 feet. In other words, the resultant force corresponding to this trapezoidal distribution acts at a distance of 4 feet from the left end of the distributed load. And also note that the directions of F, F1, F2, they all go with the direction of the distributed load. So in this example, the distributed load acts vertically down, and therefore F1 acts vertically down, F2 acts vertically down, and therefore the resultant force F also acts vertically down. Now let's apply these principles to one more example, this one right here. So you can see this distributed load consists of a rectangle and a triangle, right? So you can treat this as a composite area, consists of a triangle and a rectangle, and our question is to find the equivalent force and its location. So we go ahead and divide this into a triangle and a rectangle. And this triangle has this as the resultant force F1, and the line of action of that force is going to be 2/3 from the vertex, right? So this distance, we'll call this as X1. X1 is going to be 2/3 of the height of the triangle, which is 6 feet, and that works out to be 4 feet. And then F2 is going to be acting in the middle of the rectangle, right? So it's going to be in the middle over here. And therefore, X2 is going to be 6 feet plus half of 8 feet. And that's 10 feet. And let's call the resultant of the whole thing as F. So F is basically F1 plus F2. And let's call this distance as x naught. So here are the calculations for the resultant forces. So F1 is the area of the triangle, which will be half times 150 multiplied by 6, and I get 450 pounds out of that. F2 is the area of the rectangle, which will be 150 multiplied by 8 feet, and that gives me 1200 pounds. And our resultant force is 1650 pounds. And here are the calculations for the location x naught. So you take moment of the resultant force from the left hand, so it will be F times x naught, and that should be equal to F1 multiplied by x1 plus F2 multiplied by x2. So x naught works out to be this, and you substitute numbers, and I come up with 8.36 feet for that.